where we continue with electrical power. Dr. Ken here with you. So, in this lesson, we're going to explain electrical power and ways of finding the power taken by an electrical load in particular. So, a bit of an extension on part B. The contents part of the textbook we're going to use is 4.3 and 4.4. So, electrical power, and then we're going to get into the modelling system, the transposing of power equations. Remembering, of course, that all the maths, all the Ohm's law we use around these attributes are just ways of representing the physics, and it's important that we learn how to use them, but it's also important that we get to understand how the physics operates. So from our previous lessons, we've discovered that electrical power is measured in watts. 1 watt of electrical power is dissipated in a resistor when a voltage of 1 volt causes a current of 1 amp to flow through that resistor. So again, a lot of ones again, seems to work that way. 1 watt of electrical power, so 1 capital W, is dissipated in a resistor when a voltage of 1 volt causes a current of 1 amp to flow through that resistor or that load. It doesn't have to be a resistor, it could be some other kind of load. But whenever 1 volt causes 1 amp to flow, then 1 watt of energy has been dissipated. By Ohm's law, the resistance of the circuit is often 1 ohm as well. So if you have 1 volt creating 1 amp, you'll find it's 1 ohm and 1 watt. So the equation for electrical power is simply the voltage multiplied by the current. So that's the important part. That's the new aspect to Ohm's law that we're now adding. Power equals voltage multiplied by current. Or P equals V times I. Quite often we'll just say VI because again the multiplication is assumed in the algebra if there's no multiplication symbol. So P equals VI. Where P is the power in watts, V is the voltage in volts, and I is the current, of course, in amperes, which you probably well and truly understand by now. So here's a little example to find the power. So in this little example, you can see we've got 1.5 amps. The circuit has a lamp in the circuit and 24 volts across the lamp, which is being provided by a battery. So I'll just turn the pointer options on. So I've just described the circuit. So there's the circuit diagram and the connection diagram. You can see here our ammeter. Again, ammeter always in series with the load, up through our load and back to the battery, and our voltmeter connected in parallel. So just to reiterate, 1.5 amps and 24 volts. And of course, we know that power equals V multiplied by I. So here we have a voltage of 24 volts, a current of 1.5 amps, and if we do the multiplication, we have 24 multiplied by 1.5 tells us that the lamp is emitting 24 watts of work is being done. So the work is 24 watts of work. Now, that work, part of the power is coming out in heat because it's an incandescent lamp, and some of the work is coming out as light. So there's actually two energy forms happening with incandescent lamps. You're getting heat and light, and you're getting X watts of heat and X watts of light. At the end of the day, the total is 36 watts. So, transposing the power equation, I've also dropped in the formula wheel, or the Ohm's law wheel, which now has power, or we always did have power. I've been using the same wheel, but we always knew how to find Ohm's law with current, Ohm's law with volts, and Ohm's law with resistance. But now we're introducing Ohm's law with the power attribute of Ohm's law. So you'll notice in all these other formulas, we've now got power. There's a relationship to power. So you'll notice every single one of them. So we're moving up from the standard 3 equations for Ohm's law, and they've now all got a power component. So can we transpose the power to get the other 3 equations? Yes, well, we certainly can. So we've got the first equation, power equals VI, which is the one we've just introduced you to. We've got volts equals power divided by current, and that's this one here. We've also got current is power divided by voltage. So if we find the current, there's power divided by voltage. So let's go through the process of actually transposing the power equation for voltage. So if I want to take this equation and I want to transpose and make voltage the subject of the formula. So we want to make voltage the subject of the formula. So nice and easy, just divide both sides by current. So power divided by the current is equal to the voltage times the current divided by the current. I've simply divided both sides by current. Current on current equals 1. Anything times 1 is itself, so they eliminate each other, and we end up with voltage is equal to the power divided by the current. Nice, simple, straightforward transformation. And you can see there, that's what we've got in step 2. Step 3, we're simply making current the subject to the formula. So again, if I take my power equals V multiplied by I, and I want to make I now the subject to the formula, I simply divide both sides by V. So V divided by V, V on V equals 1. So we can eliminate that, and we end up with power on volts equals the current, which is this formula here. So again, quite simple, just a 3-element equation, relatively easy to transpose. So we've done it for current, we won't go through that again. There's also the power triangle. If you have difficulty in remembering the Ohm's law wheel, and most students have a equation sheet that has that all on them. So you can use the power triangle, and again, just cover up the item that you want to make the subject of the formula. If you want to make P the subject, cover up the P and it's V times I. If you want to make voltage the subject of the formula, just cover up the V and it's P on I. And lastly, if you want to know what the I is, it's P on V. So another way to remember the formula. But again and again and again, remember the formula, the maths, the algebra is just a modelling system to explain what the physics is doing. So why don't we go through a nice little worked example. If our lamp is connected to a DC source, the current through the lamp is 3.2 amps and the lamp is rated at 40 watts. Determine the applied voltage. So how can we go about doing that? It's not too difficult. We've just got to select the appropriate formula. Voltage is equal to power divided by current. Straight off our Ohm's law wheel, we know that we have 40 watts. We divide it by the current of 3.2 and it tells us we must have an applied voltage of 12.5 amps. So it's just a matter of selecting the appropriate formula that deals with the data that we have to find the unknown that we're asked for. At the end of the day, here's the data, amps and watts, and we've been asked to find voltage. So what equation does that? It's just a matter of looking at your equation, see, and finding the one that has those three elements and transposing it if you need to, or maybe it's already in the correct form. Example 2, what current is drawn by a 750 watt heater when connected to 240 volts? So again, we're given power in watts, we're given voltage, and our unknown is current. So we need a formula that deals with current, power and voltage. So again, that is current is equal to the power divided by the voltage. So we take our power at 750 watts, divide it by 230 volts, and that's going to be caused by 3.26 amps. So we have 3.26 amps going through our circuit at 240 volts. It will produce 750 watts. That's what the physics is doing. Now our numbers get very large and very small, and we've done some of these prefixes before, but let's just do a little quick reminder of our prefixes, particularly when it comes to power. So we've got the term here, and again I'll start in the middle. So here at unity, here in the middle somewhere, we're in simple nice watts, just plain watts. But if we want to go up and we've got thousands of watts, then it's called a kilowatt. And we use small k, big W, and it represents thousands of watts. And it can be written as 1 kilowatt or 1 times 10 to the power of 3, representing those thousands. Going up another one, we've got the megawatts. That's, as its name implies, millions of watts. Capital M, again, millions of watts. That's 1,000,000 watts. It can be written as 1 capital M, capital W, 1 MW, or 1 times 10 to the 6, the 6 representing the 6 zeros. That represents 1,000,000. And then our last one in this direction is the gigawatt. So the gigawatt is 1,000 million. So if we had 1,000 million watts, it would be a gigawatt. So that's 1 times 10 to the 9. Oh, there is 9 zeros. You can see there is 3, 3, 3, making up 9 zeros. Let's go in the opposite direction now from unity and go down, and we've got the milliwatt. small m, big W, that's a thousandth of a watt, or 0.001 of a watt, written as 1 MW, or 1 times 10 to the minus 3, because we're going down smaller, it's minus 3. And then our last one in the prefixes is the microwatt. Small mu, large W, and of course it's a millionth of a watt, or 0.00001 of a watt, written as 1 microwatt, or 1 times 10, again minus 6, to represent millionths. Power and energy ratings. So energy equals joules, if you remember, and that equals power multiplied by time. It's also exactly the same thing, but expressed in different units. Energy is kilowatt hours, and that's simply kilowatts multiplied by hours. A little trick for those of you who might be new to electrical units. The units often tell you the formula. So that is simply thousands of watts multiplied by hours. That's what it means. I'll just get rid of the writing. So here we have a sunbeam nameplate on a heating element of some kind, probably a little electric fry pan, and if you'll notice, it's operating at 230 volts, and it's 2,300 watts, or 2.3 kilowatts. So that could be written 2.3 kilowatts. If you were to run this for 1 hour, then it would be 1.3 times 1 equals 3.2 kilowatt hours. So kilowatts multiplied by hours is our standard unit of electrical power consumed. It gets used again and again and again. You can have watts per minute, watts per second, all of those kinds of things, but the most typical one is kilowatts per hour, thousands of watts per hour. So here's a little example to get into our heads a little more clearly. An electric heater is rated at 2,500 watts, is switched on for 2 hours. How much energy does it use? In joules and in kilowatt hours. So here it is in joules. Remember, energy equals power times time in joules, but when we're talking in time and joules, we're working in seconds. So in this particular case, just turn my pointer back on, we've got 2,500. It's on for 2 hours, multiplied by 60, multiplied by 60 again to get us into seconds. So that's all this thing does, is turns our 2 hours into seconds. And if we know what the power is in watts multiplied by the seconds, it turns it straight into joules for us. And we end up with a lot of joules. So it's 18,000 joules. So 18 kilojoules, or we could have actually called it 1.8 megajoules, would have been just as effective. The next one, if we do it in watts, so for energy in kilowatt hours, it's simply going to be kilowatts multiplied by time, but this time our kilowatts is in hours. Remember, it's in hours, not seconds. That's the only big difference here. So we're now in hours, so it's simply 2,500 multiplied by 2 tells us that we've consumed 5 kilowatts over that time. So that's the end of lesson 4, part C. Hope you've enjoyed learning a little bit more about electrical power being measured in joules and measured in kilowatt hours.